This is part 2 of the 2.4 notes on macromolecules. We're continuing our discussion with the second kind of macromolecule called the lipid. Before we get to that, a little bit of a review from last time. Looking at these three diagrams, which of the following would represent a polysaccharide? Again, remember what the prefix poly means. Our next kind of macromolecule is called the lipid. Lipids, like carbohydrates, are made out of carbon, hydrogen, and oxygen. The difference, however, is lipids do not have that 1 to 2 to 1 ratio. So remember, carbohydrates have 1 carbon to 2 hydrogens to 1 oxygen. Lipids do not. Lipids will have a tremendous number of carbons and hydrogens and very few oxygens. Typically, lipids are described as fat molecules, although fat is only one kind of lipid that we find. But typically, when we talk about lipids, we are talking about fats and oils that you would find in both plants and animals. Lipids have a variety of functions in the body. One of their most important functions is to store energy. Carbohydrates provide fuel for the body, but they get burned up very quickly. Lipids, however, can be stored for long term. So if you are, say, a bear and you're going to hibernate for several months during the winter, you would build up several layers of fat tissue, which is comprised mostly of lipids, in order to fuel your body for that long sleep. Other functions that we find for lipids is that they serve to insulate the body, help protecting us from the environment, whether it gets too hot or too cold. A layer of lipids is a good means of insulation against the environment. We also find layers of lipids in terms of fat tissue surrounding certain organs, and this helps protect the organs from damage. For example, your heart has a layer of fat surrounding it because your heart is constantly beating, so it needs a layer of cushioning to protect it. We also find lipids in the form of signaling molecules. When your body needs to send messages from one cell to another, it will often use chemical signals, and lipids are just one kind of chemical signal that they would use. An important feature of lipids are that they are not soluble in water, meaning they won't break down in water. This is what allows lipids to remain in the body for long term. The building blocks of lipids are glycerol and fatty acids. A glycerol is actually a type of alcohol molecule. If you remember when we were talking about carbohydrates, we said the ending ose, O-S-E, is an indicator of a carbohydrate or a sugar. Well, the ending ol, O-L, is the indicator of an alcohol. Now, in chemistry terms, an alcohol is simply a chemical compound that has hydroxyl ions attached to it. That is the OH. So if you have a carbon compound with some OHs attached, that is chemically an alcohol. So glycerol is a 3-carbon molecule that has 3 hydroxyl ions attached to it. The other component of a lipid are the fatty acids. Fatty acids are long chains of carbon and hydrogen. And at one end, you're going to have what is called a carboxyl group. This is a carbon with 1 oxygen double bonded to it, and then a hydroxyl group on the other end. Fatty acids come in 2 varieties, what we call saturated fatty acids and unsaturated fatty acids. Saturated fatty acids have the maximum number of hydrogens that you can fit on a chain of carbons, meaning that every single carbon atom is going to be bonded to as many hydrogen atoms as we can fit. And this means that all the carbon atoms are only going to have single bonds. So one carbon is going to be single bonded to another carbon, which is single bonded to another carbon. This opens up the maximum number of valence electrons to then, in turn, bond with hydrogen. An unsaturated fatty acid is where you have at least 1 double bond between one of the pairs of carbons. What this does is it takes away one potential bond that could be holding a hydrogen, but is instead now bonded to a carbon. In unsaturated fatty acids, because of this double bond, you're typically going to be finding that it's bent. This means that unsaturated fatty acids have a harder time being compacted together with other fatty acids. The most common type of lipid that we're going to find in the foods we eat are what are called triglycerides. Again, thinking about root words, the prefix tri means 3. So a triglyceride has a glycerol and 3 fatty acids. These triglycerides come in 2 main varieties, what we would call saturated fats or unsaturated fats. The saturated fats have 3 saturated fatty acids attached to your glycerol. These tend to be solid at room temperature. So fat that you might find attached to a steak or something like butter is going to be a saturated fat. The other kind of triglyceride would be an unsaturated fat. This is where at least one of the fatty acids is unsaturated. We're going to have at least one double bond with one of those fatty acids. Again, this is going to cause the fatty acid to bend. Unsaturated fats tend to be liquid at room temperature. So think about like your vegetable oils. These are unsaturated fats. This is because the unsaturated fats have that bend which prevent the molecules from getting packed too closely together. So they're going to be more loosely packed and they're going to be liquid at room temperature. Whereas the saturated fats are nice and straight, so we can pack those really tight together. So they're generally going to be more dense and solid at room temperature. So the next question, which kind of fat is considered the healthy fat? Would this be A, the saturated fats, B, the unsaturated fats, C, the trans fats, or D, none of the above because no fat is healthy? The correct answer here is B. The healthy kind of fat is the unsaturated fats. We do need a certain amount of lipids in our diet. Too much fats in our diet can be unhealthy, but we do need a certain amount of lipids in our diet normally. And the best kind of fat for our bodies to take in are these unsaturated fats. Gram for gram, you're getting less lipids in an unsaturated fat than you would in a saturated fat. And it's much easier for your body to break down unsaturated fats than it is to break down the saturated fats. Now you might see talk about how bad trans fats are. Trans fats are where you take an unsaturated fat and you basically bubble hydrogen through that fat and it forces that double bond to break and become a saturated fat. So these trans fats are transformed saturated fats. These are extremely unhealthy for your body because they don't occur in nature. So your body has a hard time figuring out how to digest these things. And as we mentioned before, the body doesn't like to waste things. So if you eat trans fats and the body can't break those trans fats down, the body assumes, oh, well, we need to store this for later. Maybe we're going to hibernate. So the body stores that away in the form of fat tissue. Again, fats are not necessarily bad. It's just that when we think about how we eat and the foods that we consume, we need to take into consideration how much of the healthy fats are we taking in versus the unhealthy fats. And it all comes down to a matter of balance. You need to have the right balance in your diet to stay healthy. Now, another very important lipid that we find in each and every one of our cells is something called a phospholipid. What we would do is take one of those triglycerides, remove one of the fatty acids, and replace it with what we call a phosphate group. A phosphate group is a phosphorus plus 4 oxygen atoms. Now this phospholipid has some interesting qualities. The head of the phospholipid is where we have that phosphate group. This is hydrophilic. Remember, to be hydrophilic means that it loves water. The tails, the fatty acid side of this lipid, are hydrophobic, meaning that they hate water. So this creates a molecule with a dual personality. One side loves the water, one side hates the water. And if you take a bunch of phospholipids and put them in water, they're naturally going to arrange themselves with the hydrophilic heads pointing outwards to the water and the hydrophobic tails pointing inwards to themselves. And this creates a dual layer. This is the structural material that makes up the cell membranes that surround each and every cell of our bodies. This is a very important component, and we're going to spend some time talking about the cell membrane and how it works later on in Unit 3. But again, when we talk about lipids, we can't just say fat is bad, because these phospholipids are an essential part of the structure of your cells. The next question, the tails of the phospholipid molecule is said to be hydrophobic. Again, what does this mean? A, it likes water. B, it breaks down in water. C, it absorbs water. Or D, it dislikes water. Finally, another kind of lipid that we need to pay attention to are what are called steroids. Steroids are a kind of lipid that has a complex ring structure. So most steroids have multiple carbon rings attached to them. Steroids are used in the body as a signaling molecule. So when the cells need to send a message from one cell to another, they will often release chemicals. Since lipids don't break down in water, steroids make a very good chemical for sending a signal because it's not likely to break down in the watery environment of the body. So we can send this signal and the signal will persist. So what happens is if one cell has a message to send to another cell, it's going to release these steroids. When that other cell detects those steroids, it generally is going to release its own steroids. And this causes a chain reaction which creates an amplified message throughout the body. We have a couple examples of steroids pictured below. The first one is cholesterol. Now you might hear people talk about cholesterol as a bad thing, especially when it comes to cardiovascular health, like heart health. But cholesterol is a naturally occurring lipid that is found in the body. The problem is when cholesterol builds up in your veins and arteries, it can cause blockage. And this blockage can then lead to problems with your circulation, but also especially problems with your heart. Cholesterols naturally help keep the body moving and flexible. We find cholesterols built into that cell membrane that we talked about earlier. The other two steroids that are pictured here are testosterone and estrogen. These are commonly referred to as the sex hormones. These are two very important signaling chemicals that help determine gender-specific characteristics in animals. Testosterone is known as the male hormone because males tend to have higher levels of testosterone. And estrogen, which has a derivative called estrogen, is considered the female hormone because females generally have higher levels of estrogen in their system. Now, to be clear, both males and females have both testosterone and estrogen. The difference is going to be the balance that they have in their bodies. Kind of a famous example of testosterone versus estrogen is that in lions, male lions have that really large mane, and then female lions don't. And what we find is it's the production of excess testosterone that actually triggers the growth of that mane. So females don't produce a tremendous amount of testosterone, so they don't grow a mane. Males produce a lot of testosterone, so they do grow that mane. These sex hormones are steroids, and what's important about that is that they are lipids and they don't break down in water, which means that they can actually build up inside of the body. When a human reaches your age, adolescence, your teenage years, you go through puberty. Puberty is where your body starts producing levels of testosterone and estrogen higher than it has been, and this leads to sexual maturity. These signals start slowly and build up over time. This is why adolescence and puberty lasts for several years. So it takes several years for a human to grow from their adolescence to adulthood.